This part is a general X-ray spectrum. This is simple. For the example, is that ions. The electron energy over is determined for this free electrons. So the wave number of electrons can be exchanged to these equations. The E0 should be the edge energies. This background spectrum is expressed by the Victorine formulas we discussed yesterday. For it depends on the energy force. No, energy third. This is the main part of the this background. The B and C is very small. So before the T times, our X-ray spectrum is defined by these formulas: mu0 mu over mu0 minus 1. The mu-s and mu0 is sometimes the same after the subtract of the background. The pre-edge should be neglected. And this is clear X-ray functions of ion bulk. It's extended to the about 50 angstrom inverse. It includes to the some structural informations. And finally, Fourier transform. This sinusoidal function should be changed to the radial distribution functions by Fourier transform. The sinusoidal function is become to the delta functions, and our data is limited by the from 0 to sometimes 20 or 15s, or it depends on the systems. So the Fourier transforms overlapped of the Fourier transform this rectangular functions shape. So this has this function should be expressed by this sinusoidal functions. So the overlap of the this delta function and sinusoidal functions. So after that, resulting such kind of Fourier transforms. In case of there are two components. The first component is expressed by the sinusoidal functions, and another one is the different frequencies and different envelope of the A atoms and B atoms. So some of this spectrum has a node of this part. And after the Fourier transform of these functions, it has two peaks from the A atoms and B atoms. Actual Fourier transform of ions appears here. First peak is, of course, the first nearest neighbors of the body-centered part. And the second one is here. For the BCC systems, it is difficult to the first peak and second distinguish to the first peak and this second peaks. Usually, it's including these two peaks, we obtained just one peak. And the third peak is here, third nearest neighbor is here. And it is interesting to the fourth peak. Fourth nearest neighbor is very large. Actually, this peak intensities depends on the number of atoms, 8, 12, 12, 8, and distance of from the absorbing atoms. So in this case, the force peak should be more smaller, but real case is different. There is a focusing effect. The atoms are arranged to the linear systems. So the photoelectrons is focused by the center atoms, and the forward scattering amplitude is very large, 1, 2, 3, 4. So this peak should appear the very large intensities. This is a typical example of the BCC system, ions or iron rhodium or some metallic systems. This is an interpretation of the focusing effect. And the forward scattering amplitude is very large, this scattered. And this is the angle of the scattered process. The back scattered angle, amplitude is around 2 pi here. No, pi is here, pi. Usually, we analyzing to the X-axis using these formulas, single scattering and some several approximations. Normal unknown parameter is the interatomic distance and the number of surrounding atoms or coordination numbers and divival factors. The back scattering amplitude and the mean free path of the electrons, phase shift of the central atoms and back scattering atoms, they are generally calculated by some theoretical code. In this case, we use the FEFF code developed by the University of Washington's Professor John Reyes. This is an Italian conference, X-axis conference in Italy. He is dancing with my daughters. Now we check the roughly function of the phase shift and the back scattering shift. Here is the taking from the Theo's text, very old text, but very useful. So the central atomic absorption phase shift from the absorption atoms is different from the between these metal, magnesium and rhodium. But function is very simple. On the other hand, scattering atoms, this is the phase shift of the scattering atoms, carbon, chromium, and bromine here. Something complicated in comparison to the absorbing case. And scattering amplitude are very different for each atoms. Carbon, chromium, ions, bromine. The higher atomic numbers, there is some node around here. It's called the Ramsauer transient effect. So they has a different. Each atoms has a different scattering or scattering phase and amplitude. The X-axis can distinguish to the what is the surrounding atoms for the experimentalists. Of course, we fit the X-axis for the candidate atoms using the candidate functions. So we selected the most fitting parameters. For example, we fit to the surrounding atoms should be ions, or fitting is not good. So in the case of the bromiums, all fitting is best. So we can distinguish the surrounding atom is the bromine. Now, X-ray from the synchrotron radiations is linear polarized. This is very simple photoelectric waves. And using this linear polarized X-rays, the structure information can be separated to the directions. In the case of the surface X-rays, so the electric vector is parallel to the surface direction, surface. So X-rays can only the information of the surface parallel to the surface. Or in this surface, X-ray incident to the glancing angles. So electric vector is perpendicular to the surface. So the X-rays information includes only the perpendicular to the surface. Perpendicular information to the surface. But the function of the angle dependence is expressed as these equations. So effective coordination number is has these equations. So we can analyze to the atomic arrangement of the surface to the including the surface or perpendicular of the surface. Next polarization is the circular polarized. In case of the some facilities, so we change to the linear polarization to the circular polarization. This circular polarization is very useful for the analysis of the magnetic systems, the spin over orbital magnetization systems. We discussed next applications, so the magnetic system using the circular polarization. Here is the atomic absorption coefficient, the KH here, LH here. So usually the KH is very simple because the one KH is appears and the long extended part is following. But sometimes we should use the LH. For example, the lanthanoid or some higher atomic number element, we use the L3H because L1H includes to the information of the L2H, and L2H including to the some X-ax structure from the L3H. So L3H is a very simple, has included a very simple X-ax. But range of the X-ax region is very short. Usual X-ray range is about 1,000 electron volt from here to 1,000 electron volt. Its conversion in the photo wave numbers is about 20 angstrom inverse. Now, it is an interesting result. A comparison to the KH and LH. The lower energy of lanthanoid systems series. The lanthanoid KH can be can be detected by the both of KH of L3H. The amplitude of X-ax larger for LH than KH. Of course, it includes to the energy resolutions of from the monochromators or natural length, natural width. So in this case, the LH usage of LH is better than the KH. Now we move on the thermal effect. Our system is iron rhodium alloys. The first peak is from the iron KH. The first peak is iron rhodium, and second one is iron and iron rhodium. And from the rhodium KH, rhodium iron is here, rhodium is here. Vice versa. The thermal effect should be simple. More higher temperatures, the peak intensities should be degrees, because the thermal factor is appear in the amplitude of X functions, sigma divider factors, and minus part, this is a reduction function of the X signals. Of course, physically, the thermal moving diminish to the backscattered X-ray electron amplitude. So the absorption process is very fast. X-ray absorption process is very fast, minus 16 10 to the minus 16 second. Comparison to the atomic vibrations, it's 1,000 times faster. So in such a case, the thermal vibrations is snapshot behaviors. The one times electrons scattered of here, and one time electron scatters these atoms, one time is these atoms. The situation is similar by the static disorder. From the X-ray absorption atoms, sometimes it's near scattered near atoms. This is near, and sometimes scattered at the far atoms. So these two disorder, thermal disorder or thermal vibration or static disorder, include to the divider factors. But it can be distinguished to the both. So we measure the temperature dependence Xs, only the thermal vibration is effective. Short break. I show you the X-ray absorption process is very short, 10 to the minus 16th around T. So how we can estimate it over this very fast systems? The equation is here. Let's consider the classical rotating systems or rotating electrons with a nucleus. So RIF is a ratio of excitations, and tau 0 is a lifetime. So in this case, the Bohr radius is here, and the electron energy emitted to the h bar omega as energies. Alpha is we discussed yesterday in fine structure constant. So power of electron, rotating electron, expressed by these equations, and P is the atomic dipolar oscillations. So the time constant of the one, this is the, classical mechanics power of from the concept of the classical mechanics of the electrons, moving electrons produced to the h bar omega's photons. So the time is separated is calculated by the kappa for the kappas. So it should be the 15th, 10 to the minus 15 second. So the speed of or times of the X-ray absorption process can be calculated by the classical rotating electron systems. Now, we just back to the temperature dependence of Debye-Euler factors. The simple model is the Einstein models or the harmonic vibration models. The potential is expressed by the Einstein frequencies, and the displacement of the central stable distance are 0. And in this case, for the Einstein models, the Debye-Euler factor should be expressed by the cotangent hyperbolic functions of temperatures. So this is an example of from the ions, the temperature dependence of the Debye-Euler factors for first nearest neighbors and the second nearest neighbors. This analysis should applicable to the harmonic systems, but usual realistic systems has a harmonic effect. That how take into account to the anharmonic part for the X-as analysis. So now we show you the anharmonic analysis to the X-as thermal vibrations. There are three. We consider the three approximations. First is the thermal average of the exponential functions. So our X-as function theoretically comes from the exponential part, real part of the exponential functions using the derived by the Fermi's golden rule. So it is very convenient to the cumulant expansions for thermal average of the exponential function. The second expansion is approximation of the atomic potentials. Of course, the harmonic potential is a non-perturbative part, but we take into account the anharmonic part by the perturbation expansions. Third one is calculation to the cumulant expansions. We use a field theoretical approach, Feynman diagrams of the thermal approximations, the quantum statistical method. The equation is here. The X-as functions can be expressed by these sinusoidal functions we already discussed, but there is no thermal average part here. So we set the thermal average over here. Alpha, delta alpha is a displacement from the average distance. So our thermal average of our function is concentrated to the thermal average of this function. Now this exponential function is expanded to the cumulant expansions, and there is several cumulant here. Delta alpha is the displacement. It has this dimension of length. the first order accumulant, second, third, fourth order accumulant is there, and these are we call the moment. So just the second order accumulant has this square of the displacement of thermal average of the square of displacement. This is the not usual Debye-Order factors. In this case, the second part is neglected. This unharmonic part includes to this part and this part, this part. So the harmonic approximation, we use only these terms, and for the unharmonic analysis, we should take into account of this part or this part. And it is interesting to this first order accumulant has a k first dependence, k order 1 dependence. So this effect is not distinguished with this average length. Also same the k first dependence. Actual analysis of the unharmonic part, we expand to the interatomic potential by the step by step. So first one is the harmonic part, and the third orders, fourth orders. In the case of the most potential has like systems. The equation of the most potential is here, and expanded to the this exponential part is here. So this part should be the harmonic part, and this is the third order, fourth order part. And how calculate to connect to the accumulant to this coefficient of harmonic potential? The Feynman diagram is very convenient. For example, the second order part accumulant has this diagram and so on. Third order accumulant has this diagram, so on. So in the harmonic part, so second order accumulant has this part is this V2 is come from the harmonic part of the potential, coefficient of the potential. And this second order accumulant includes also the fourth order coefficient from the potentials. So in case of the unharmonic potential, second order accumulant is not already only the harmonic part. The fourth part, maybe six and higher orders. And the third order accumulant includes the very simple diagrams here, and it includes also the third order coefficient from the potential. But the next orders include the third order and the fourth order. It's very complicated. So the fourth order includes the fourth order. So usually we also we use just the lowest orders. This is a very simple. Second order accumulant is equal to the second order coefficient. Third order accumulant is equal to the third order potentials. Fourth order is also to the fourth order. Connection between the accumulant order and the coefficient order of potential is very simple, becomes simple. Realistic actual calculation includes the more complicated systems, but the resulting after some approximations is very simple. Now, we discussed the reduction factor of the X-as functions. The by-order factor is also reduction factors, thermal reductions. Next reduction factor is the intrinsic loss. We write down to the usually S0 squared. The multi-electron excitations, there is many electrons, the intrinsic inside of the atoms. The 1s electrons goes to the continuous state, but electrons go through to the another shell electrons. But we summarized this complicated systems of this just parameters. The reduction factor is very close to the lower than unit, so it depends on the atoms. Several typical value is 0.7 to 0.8 on here. It depends on also the photoelectron energies case, and first and 0.8. This loss process is an intrinsic loss, the inside the atoms. The electron mean free path lambda is called by the extrinsic loss. After the excited to the lone atoms. Example of the electron extrinsic loss includes to the lifetime of the photoelectrons in free path. Useful algorithm, useful method calculated to the mean free path is Penn's algorithm, or this method calculated to the these lines. The electrons of energy of electrons and the mean free path is here. So lower energy is the electron mean free path increasing, and the higher energies it's increasing as energies of linearly. So lower energy of electron has a long mean free path. That is the reason because the Zarnes has important multiple scattering effect. So photoelectrons lives long times, so the multiple scattering is very effective for the lower range of fine structures. In case of the nanomaterials, especially metal nanoparticles, the plasmon excitation is very effective. The plasmon we discussed yesterday is a plasmon is a special character of the nanoparticles. So in case of the nanoparticles, the mean free path is affected by the plasma excitations. We discussed the later applications. Now, finally, I show you this region, Zarnes regions, the theoretical interpretation of Zarnes region. The Zarnes regions is very complicated to interpret. X-as is very simple, using the back scatterings, the one single scatterings over sometimes multiple scatterings. The Zarnes region is complicated. First interpretation of Zarnes regions, or the excitation of the quasi unoccupied place. We discussed before the tea times. If there is an unoccupied state, here absorption coefficient jump very sharp. There is a nice peak, sharp peak before the edge. But in case of the very close to the these areas, the quasi unoccupied level appears around here. So this concept is from there. This is the aluminum KH. After the excited to continuum state, but there is some energy levels. So in K2 or some band calculations, the peak intensity is assigned. In the case of this is a model calculation, rock salt and zinc brine. The fit is not good, so experimental. But the ultralight type atomic arrangement, the peak is quite coincide of the experimental one. This is one calculation of the one interpretation is from the Zarnes interpretation. The second one is the full multiple scatterings. Of course, in the X-axis regions, multiple scattering, threefold, four times, fifth time is important. But in case of the Zarnes, the full multiple scattering calculation is important. The scattered, so almost infinities. Not realistic, not infinities, but calculation is very simple to the infinities multiple scattering. So in the case, this is American group of the calculation for this perovskite titanite. Only it takes into account only one shell, first shell. The peak Zarnes structure is here, and 3 shells, 4 shells, 5, 6 shells, 6 shells. Comparative to the more shells and electrons scattered the infinities. So if we take into account the 6 shells, the calculation result is close to the experimental result. There are 2 interpretations solved to the Zarnes regions, band electron excitations and multiple scatterings. Now we summarize to the Zarnes and the X-axis. Zarnes include to the 3D structures because long mean-free path, the multiple scattering is effective, so the every real positions information includes at once. And electronic state or valence state is applicable. And of course, the theoretical calculation of Zarnes is very difficult, but it is usable to the fingerprint, as a fingerprint. The standard model is here, and our unknown spectrum is here. So which is the fit, which is fitted. Oh. And the 2 theoretical approach exist band pictures and multiple scattering pictures. On the other hand, the X-axis is quite simple, but only one-dimensional structures because the single scattering process should be dominate. Of course, the higher orders double scattering, triple scattering is included, but this is the very weak signals. With a very accurate technique for the interatomic distance is very, the error is these levels, and the coordination number is a little bit higher error, but 10% is accuracy. And I show you the last part. The thermal analysis is very effective. So the dynamics or chemical reactivities, we can discuss this. I show you the later application of these systems. So ZANES has more information, but the analysis is complicated. XRS is very simple, but information is very small, but accuracy is very high. This is the final one. And I introduced to the YouTube book and the website of the XRS finally. The tail text is very historical text, very old classic one, but the information is very useful up to now. And the Koningsberger is a very big book. I introduced to the Banker's textbook. Or recently there are some textbook written by English up to date. Of course, the website of FAFF is useful, and IXSAS, International X-ray Absorption Spectroscopies, in the website it has a much informative. So please visit that website. The registration is free, so you can easily obtain the information. Okay, now I've finished the lecture 3 before the lunch. And tomorrow we discuss the applications of nanostructures. This afternoon, just I discussed how to move the analysis real systems, and Professor lecture XRDs. Okay, if you have any questions or comment, we can discuss before lunch. Any questions or comments? The XRS analysis. If you like to calculate to the field theoretical calculation, if you like to the field theoretical calculation, the Feynman's diagram is also very important, interesting for exercise for you. Yeah. This review paper appears of this type of calculations. Are there any questions? Okay, if not, we should take a break for lunch. Of course, if you have personal discussions, we accept. Thank you.